So now we move to the third module of machine learning in a nutshell. So we already covered data and task. Now let's come to representation. So what I meant representation, it related to the F, it also related to the X. So it's an issue like actually coupled related to both the function and also your data types. So for example, I can give you this example is you have this text input like that piece of text, the Amazon review, right? The scikit-learn needs to take something like a matrix form. How can you convert the different Amazon reviews, they're in variable length, they're all discrete, into this tabular or matrix form? So very classic trick. I mean, before the deep learning, people use this trick called bag of words trick. So they just represent every possible English articles using the English vocabulary. So you can think about this is our vocabulary of English language. It's actually fixed, right? We can almost fix one because there's a shared vocabulary there. And then I actually just can represent every document as the frequencies of the words appeared in that document. And this is a very classic way to convert those type of variable lengths or discrete data inputs into numerical, because this is const, right? When it's const, numerical, and this scikit-learn type of library can directly work on it. And so it's, in fact, this bag of words trick is not just for a symbolic or sequential type of inputs. And before the deep learning 2012, the winner of ImageNet competition mostly used this idea called bag of zero words. Which is really interesting. So this is about classic representation. Then people shift from feature engineering to feature learning. So before 2012, the ImageNet challenge, the majority of the task or the time spending by the applied machine learning scientists is on designing the domain-specific features. And they are mostly handcrafted and task-dependent. In 2012, the ImageNet challenge actually paved a way of what type of features are good and also almost universal for the imaging data. And recently, the transformer type of model paved the way of what's the universal feature representation for the language type of data. And also in the recent few years, the graph type of data, it's also got revolutionized about how to represent graph data through this graph neural network technologies. So in the end, people shifted from feature engineering to feature learning because they are easily adaptable to new similar tasks. And the different kinds of model and what representation fits what really depends on the data types. So this is the fundamental reason why I categorize our lectures according to data types, because I want to cover more about the feature learning state-of-the-art method. And they are, for different type of data, they're popular and dominating method representation and architectures for different kinds of data. All right, so again, so this in fact is before deep learning, and there's something called the kernel method, and they try to solve something very similar, like I said, right? When you have discrete or very complex X input, more maybe there are different shapes, there are graphs, sequences, or 3D structures. How do you represent them in a computer? And this graph, this kind of kernel method, it's the fundamental philosophy behind is similarity. So we're going to have a short section to cover this because they are really classic. All right, then more, it's the recent deep learning base. There's this multi-layer learning, supervised embedding, layer-wise pre-training, and then to again emphasize the 2012, this era starts of AXNet, almost the same as the 1998 the LearnNet 5 that Yang LeCun invented in 1998. So it's really a return of something invented in 1990s. But hopefully you still remember what we covered in the first lecture. There's reasons why it's now, because there's huge amount of training label data. There's also this really great GPU computer architectures make the training and testing feasible for this humongous and really large type of models. All right, so let's move to scoring function. So we already covered this, right? So just revisit, what do I mean scoring function? It's really that function measure the differences of fxi and yi, the L function. So there are really different kinds of L functions. Just to give you an example, something called hinge loss. And the hinge loss, we're going to cover that later. So it's a really weird form, but there's a reason behind this form. So just remember, so it can be just, the simplest can be just maybe yi, xi minus yi, maybe take an absolute, or maybe fxi minus yi, take a quadratic, but there's also some other kind have a more special form, like some kind of max function, upper bounding it. And very big thing I want to cover in this kind of loss function, it's regularization. So we already said, right? So our binary classification, the purpose to look for a line, decision line, separate the blue and the red very well. But if you look at this graph, there are many, many lines can separate the blue and the red very well. Who is the best? So this L2 regularization based idea is trying to tell me, I'm not looking for a line anymore. I'm looking for a band, a region separation that I try to separate the blue and red using a band. That band is as wider as I can. And this gives me a very good classifier that has better generalization properties. Okay, again, remind yourself, what do we mean generalization? It means future points. It's not just the training point, it means future point. To be able to find this kind of maximized wideness band, and in fact, you just augment your training data, your training loss, with something called L2 norm on the parameter on that slope vector you need to look for. And we're going to derive this and tell you why. So what do this L2 norm even mean? So from a semantic view, it just means I'm looking not for a decision line, I'm looking for a decision band, decision region. And you can actually prove it. It works it has really great generalization ability, especially on the small, when you have small number of training data. All right, so now we go to search. So the search, it's actually very interesting and there's many things involved, but I will cover mostly just gradient descent. And the reason why we cover gradient descent is, so in the end, it's because this large scale consideration. So when your data, it's not, you need to consider, is it training data or testing data? There are different kinds of solutions. But when the size varies from thousands to millions to billions or even to trillions, and it really shifts the purpose or shift the focus of the algorithm design to a different paradigm. It's a different mindset. So keep that in mind. What type of problem you're solving? What's the scale of your current task? And keep in mind, always calculating time complexity, RAM complexity, space complexity. Those will help you in the long run. All right, so we're going to cover gradient descent. I will not cover this, but just give you a flavor. So gradient descent, almost like starting from this point and then trying to find the middle point on this loss landscape. But there are many like badly behaved. There's many things you have to do to control that. Control from this random starting point, how to reach the middle point. So we're going to talk about it. And there's many things called plotting the loss curves and like the X train and the Y train. The one I just showed you, I don't plot this curve, right? But when you truly start to code your own like version of those algorithms, you're going to understand why this kind of loss curve loss landscape is important. And then these are all various bias and variance trade-off. People will talk about it. We're going to cover that. Again, last few page. I really want to finish this to have a clean stat next time. Last section is about models. And then again, this pipeline and what we use so far is just to measure the prediction accuracy on test data. And there are many, many definitions of metrics, which I already show in that dry run Jupyter notebook. And in there, we showed precision, recall, and F1, but there's also a lot of classic metrics. They cover different, they care, in the end, they measure different type of prediction, different type of preferred predictions. All right, so beyond prediction performance, there's also a lot. In fact, in our CS department, the majority of the machine learning faculty members are not focused on prediction accuracy anymore because we are actually pushing for that, but we're also pushing a lot other type of properties like theoretically sound, trustworthy, efficiency and fast, explainable and communicative. So those are other type of, and also fairness. I don't put it here, but there's a very big proportion, a lot of grad students working on fair models. So these are something like to keep in mind. And my group actually has a lot of work on this sensitivity or robustness of the machine learning models. This is the most classic example that pinpoint this issue. So you have a panda image like given to this classifier, it predict as panda. So this is the predicted fx. And then you just add a smaller delta, and then this is the delta. So you just somehow your eyes will still treat this image as a panda, but this classifier will classify this very shortly as a gibbon. So if you think about it, wow, how can this really smart deep learning classifier making mistakes like this, right? This sounds like stupid. Yeah, indeed, because this landscape you learned are very sensitive, and the sensitivity itself is a very important property. We want our learned F model to be stable, and that's the property actually my group has a few students work on that. All right, I think this is everything, and this is our sectioning of the course, and we focus on tabular data. So we first focus on tabular data, then we focus on 2D imaging data, then we shift to tabular data, but more advanced supervised learning, and then we move to 1D sequential data and focus on generative and deep learning models. And then the last section is the non-supervised models. And your homework is also designed accordingly. And please visit the website, and if you want to get a rough idea what are this planned schedule.